welcome to this webinar. Happy to have you here today for pixel streaming or Unreal Pixel Streaming and OKE. And we have some fun stuff to show today. Pi Day is going well so far, and yeah, lots of fun stuff today. So, real quick overview on the call today. Have myself presenting, Matt Vander Vilet, and some collaborators, colleagues, and conspirators on this project, Serge and Adele as well. Happy to answer questions and direct you into some more information. And then real quick, just a little Pi Day trivia here. I guess the characters 2022 appear at the 17,953rd position in the number pi. So that's today. Good to know. All right, so I think we'll kick off. We'll have plenty of time, I think, at the end for questions. But feel free at any time to put stuff in chat or Q&A, and Serge it down. Myself can look at that monitor and what have you. So yeah, again, welcome to the Pi Day event. Glad you're here, and really hope you have a great time throughout the day. Feel free to share however you like throughout the day, and join our Slack channel. We can paste that full link in the chat here for everyone to click through or just type in. Always easier that way. So yeah, again, welcome. So in today's kind of topic in this webinar, we're kind of just going to go over in general a little bit of background. What is pixel streaming? Cover a little bit about integration with data and use cases, which are many, and then kind of get into really the nitty gritty of it. So the basics of the pixel streaming runtime, what that looks like, some of the subcomponents like WebRTC, and then how we took this and designed for Kubernetes, and all of which we'll wrap up in a demo, and pick apart and look at things like the cluster itself and what we have running on there, and some of the specifics there. And then again, plenty of time for Q&A at the end. So think about questions and stuff as we go. All right. So I am, again, Matt Vander Vilet. I'm a principal cloud architect here at Oracle. Really have a background in cloud native web apps, but in a nutshell, I like to tinker, right? So I like to play with new technologies, try them out, translate them to modern architectures, and do all that stuff that goes with that. So I'm sure many are familiar here. Okay, so I'm gonna try to slow down pretty good here and cover at a high level what is pixel streaming, and where this came from, and how it's kind of what it's doing, right? So in the left column here, we have sort of a look at the how this transcends from the product side. So Epic Games is the interactive entertainment company, has been around for a very long time. They're ultimately the provider of Unreal Engine, which is widely developed, a widely adopted 3D engine for game development. One of the more popular ones on the market. Spans a multitude of use cases in industries like film, architecture, automotive, manufacturing, gaming, of course, simulation. And then pixel streaming is, boils down to a plugin that they've developed that they can integrate with their experiences, the unique applications built on Unreal. And it, in a nutshell, is a way of kind of offloading the rendering and encoding of the game itself, or the application itself, into a live media stream. So that media stream, according to the specifics and how the experience is designed, can have user controls, so user input controls, very much like watching a video, except that the stream is playing back all the rendered frames and audio generated by Unreal in the application, instead of a pre-recorded video clip. So as you can imagine, right, this is a live encoding. It takes a little bit of horsepower to do that, and that's where our GPU and everything comes into play. And then the users can interact with this video stream or media stream, controlling it from their browsers, sending keyboard, mouse events, touch events, or custom events emitted through the web page, all back to Unreal Engine, driving the experience. Kind of under the hood, it uses a WebRTC peer-to-peer communication framework, really to establish the lowest possible latency between the user and the Unreal application. So, effectively that means that we're directly connected to that streaming application, that Unreal app, and that gives us very low latency and an experience like we would be running that on our machine itself. So ultimately, this avoids any real special requirements on the user's machine, and modern browsers is effectively all you need. So we'll kind of talk about a little bit of the benefits of how this pans out and how WebRTC applies in the next slide. So yeah, very good. All right, so as I was saying, right, we separate the user device and the GPU and the CPU that are running the application, encoding it, rendering it, and streaming it ultimately. So the benefits of this is that we can really support a very high quality media, complex scenes, high resolutions, depending on the application requirements and what we're trying to do. Again, as we do this, let's not think exclusively gaming. All sorts of things, and we'll get into some of those use cases in a minute here. So the rendering, visualization, performance, are all met with the NVIDIA GPU that's selected or sized accordingly to the requirements of the application, and that can vary, right? Just like anything. So once again, the end user ultimately then doesn't need to download or install anything special. They just use the browser, and that makes the application very portable, right? On my laptop, I could do it on my phone or tablet. Doesn't really matter. I'm just relying on my cloud resources for all that rendering and encoding. So yeah, the other benefit is that part of the build and the compilation of the package doesn't require or doesn't have special hardware requirements, right? We're offloading that also to the cloud. So we don't have to package or distribute binaries for the end user of the game. They don't need to download large executables with all these scenes and other meshes that might be pertinent to the experience. It can all be contained within the cloud. And yeah, once again, the WebRTC really gives us that direct connection to that streaming machine, and in this case, a pod, and establishes very low latency accordingly. And what's a little bit subtle about it is that there's, we think about these experiences, they're very visual, immersive, and 3D-like, whether we're talking AR, VR, but there's also a live data channel that is available between the game itself to the end user and vice versa. So think of it a little bit like a WebSocket, except it's really a direct connection. So this data channel is great for sending data or events straight into the application for processing in whatever way it might want to process or need to process. Now that we've covered a little bit about the high level of what pixel streaming is and how WebRTC really enables this, we'll talk just quickly about how data can be integrated and some use cases around pixel streaming beyond just gaming. So really, what is the role of data in these experiences? I mean, we have gaming, simulations, digital twins, complex data visualization. Really, it's the differentiating part of the experience and how you design these applications. So pixel streaming really makes the act of enriching enterprise data into an immersive experience possible. So this is the layer where we take that data or whatever we're enriching and putting into the application for the end user, and we have a great visualization and distribution platform for that. So with this, we can imagine all sorts of things, right? Providing contextual insights and visualizations, really opening up new avenues for interactive real-time experiences. And this immersive nature of the virtual experiences is enhanced by the actual data and event feedback of the user, right? So rather than purely simulated or randomized content or static content, it can be very dynamic and contextual in the experience that the user is going through. And when we take a look at that and we superimpose these notions from cloud technologies used for data ingestion, storage, and even just events and processing, we can readily use those channels of data and integrate them into the platform. And then kind of on the flip side, right, we have this experience, a new experience for the end user, and they're touching it, interacting with it, doing what's called a glare, looking around and interacting with it in a brand new way. So we can collect analytics inside the experience of how users are truly behaving with it. We can use this to tune or cater the experience, again, with the context of the world or the application within which they're immersed. And then, kind of more traditional things in user feedback, like, measuring engagement and behavior and what they're actually touching and working with, so we can fine tune that experience later on. Okay, so with that said, just general background, right? Here are a couple use cases, and there are many, right? For how we can use data and integration into pixel streaming on Oracle. So in this first scenario, we'll talk about IoT, right? I mean, IoT is perhaps one of the most exciting opportunities with pixel streaming. At least, for me, I like this idea of immersive real-time reflection of information that's coming from the real physical world. So, whether this is different sensors or actuators, streaming real-world contextual information in real time to, cloud provider backends, database systems, event-based application architectures, ultimately all of which pixel streaming can be a consumer. So this data can be processed, analyzed, categorized, ultimately integrated right into the 3D visualization. So this has really exceptional utility in things like responding to alerts and proactive modification, real-time decision-making, simulations, digital twin type representations, et cetera. So that's just a really high level what you might envision with something like IoT. Obviously, kind of sky's the limit with how deep you're going to go there. So here are sort of another couple use case examples, just throwing out there as possibilities, right? You could imagine, with Oracle SaaS, we'd have integrations with the pixel streaming platform, offering these immersive user experiences. So, we're showing like a marketing platform and a campaign offering 3D immersive information to the target audience in the context of their surroundings. So the required information is kind of translated into these projections from the campaign, superimposed as an AR type of experience. And then another example, you could imagine an e-learning platform, similar in some ways, where but different also. So student profiles, course content could be in the e-learning platform, right? We could build this experience in Unreal Engine, where any number of or some number of students could come. You have an instructor or a teacher in the room, and you can have an interactive virtualized classroom, with 3D avatars and a whiteboard and other things that can be interacted with. So all of this, made possible through pixel streaming. Obviously, with some ideas here from other Oracle products. Okay, let's check how we're doing time. Good. Okay, so covered a couple use cases. Now we're going to dive into really the basics of the runtime and what this looks like from an architecture and application perspective. So all the while, ever since sometime shortly after pixel streaming became a plugin and was offered through Unreal Engine, they offered these kind of starter code or sample code with the basic pixel streaming components to get started, right? So anyone here on the call may be familiar with those, and we'll kind of talk about them each individually here. And then, really what happened and how this has changed is that back in August of last year, with Unreal Engine 4.27, they, and really through the contributions from some pretty smart people, they made it possible to run pixel streaming runtime or build to Linux, Linux-based GPU environments, and also Docker containers. So prior to that, basically you would build to an executable and run and operate it on a Windows machine. While that was possible to do in Oracle Cloud, it really had its challenges with operating and production readiness, right? So with this addition and support for Linux-based containers, now we really were able to kind of rethink this in a more microservice-like deployment, and took that as a realistic approach to solving this for Kubernetes. So with all that said, the basic building blocks here are Unreal Engine itself. So this is going to be this kind of block here. This is the application. This is the game that's designed, the unique experience, right? And then everything else is independent of that. It doesn't matter what that Unreal experience is. The rest of it is all just agnostic to it, and wrappers or enablers of the pixel streaming technologies. So among those are first and foremost the stun and turn services, which really offer the interactive connectivity establishment through stun and turn protocol, or TCP and UDP and stun and turn, to traverse around network network gates or firewalls or what have you. NAT gateways, and we're going to talk about that specifically in just another couple slides here. Then, with that in place, that subcomponent in place, there's Signal Server, which is our kind of peer registration and session description exchange. So this is where a player would connect and say, hey, I want to play this game, or I want to join this experience, and it's going to provide details to the client and the streamer of how to connect those two. Matchmaker, and these terms, if you're familiar with pixel streaming from something else, it's these are taken directly from Unreal Engine, and that's rather intentional, so that we have parity to those original examples. But basically, Matchmaker is like a broker, right? So when we have multiple players and multiple streams available, we have to have an aggregator of sorts, or something that makes the decision of who goes where. So that's what Matchmaker is doing. And then finally, the basic web server, which is just static content, a WebRTC player, using a basic JavaScript addition to create a kind of a shim for WebRTC, or a normalization across the board, so all the modern browsers can use the same APIs. So that's sort of the building blocks. That is independent of the runtime in Kubernetes, but that's what comes from Unreal, and how now we can start to look at this in containers is largely based on this. So before we get into that, though, we're going to talk a little bit more detail about WebRTC, which is, again, this peer-to-peer communication from the client to the server. All right, so WebRTC, we've talked about it, right? We've mentioned what it's about. This is really used in a variety of different web apps, like whether it's surveillance systems, video chat, conferencing systems like this, augmented reality, autonomous driving systems. I think even Facebook Messenger might use WebRTC in their client for the data channel component. So it's not a it's one of the less common, I guess, protocols or interfaces in web apps, but it's out there all over the place. So how does it work, right? And really what it is this pairing technology for real-time media or data streaming. In order to establish that, it uses this four-way handshake where the peer networking configurations and firewalls are traversed. And so the network is analyzed and based on that network and the way that the exchanges go between the signal server and the client, you're able to establish the excuse me, the way of connecting the user and the stream server. So ultimately this arrow in between indicated by the four. So first, both peers, the user and the stream server, register with the signal server. So we have Matchmaker, as mentioned before. Once Matchmaker is done its job, user is attached to the stream server. Signal server, gives them both connection details, and then the network or firewall traversal methods are determined. That is done through stun and turn. And then the result of that is the interactive connectivity establishment connection details. So each of these, the stream and the user, are using those to connect to one another. So finally, that transport layer is established in step 4, and the client and stream are directly connected. Okay, easy as that, right? So, again, back in August, this became possible as something to apply into a general microservices design with the containers running in Kubernetes. So we took those original constructs and samples from Unreal and ported them with some basic extensions and obviously containerization for those services into Kubernetes constructs and how we actually deploy this. So on this slide, we're showing exactly what we've concocted here. And this could certainly be different, right? So there's a lot of ways to peel this potato. But here's what we did, and we find it works pretty well. So what we did was we separated the app into 3 distinct node pools, right? So one is a node pool strictly for the turn services. These are in a public subnet, so that each of the worker nodes in that subnet gets a public IP and can be has host networking through the daemon set that the turn pods run on, and that allows each of the turn services to control all the network ports and things that are necessary in creating that ICE configuration. Next, obviously, we have our GPU node pool. So these are distinct shapes. They are it's sized according to the application, how wide we want to scale, how much each stream or each application really needs from a compute or GPU perspective. We size that pool according to those requirements. And then lastly, we have a generic node pool. And in the generic node pool, it's everything you'd expect, right? So Prometheus and our basic services here, ingress controller, other routing services, and our familiar services from Unreal, so Matchmaker and the web app, so the player view. So if you look at this diagram, actually the signal server is really the API layer into the Unreal engines. So there's a one-to-one relationship or correlation between a signaler and Unreal. It doesn't have to be that way, but in those examples, that's the way it needs to work. So in our GPU deployments, our streamer deployments, the signal server runs as a sidecar on that pod. So both basically that pod's going to have 2 containers, I think actually 3, but in any event, that third one you can ignore for now. What's new in this diagram is this proxy layer. This proxy layer provides an avenue for integration into like REST APIs or otherwise an Unreal Engine that are coming from external, right? So inside of the cluster, you could resolve directly to those endpoints without going through this proxy layer. But externally, we've built this really simple proxy layer where a service can hit APIs for individual streams which have affinity to their respective sessions or what have you. Okay, so behind the outside of the diagram, right, we have custom metrics we're collecting and feeding into Prometheus adapter for horizontal scaling of the streams, and then service accounts for system heuristics like node establishing node affinity, anti-affinity, discovery, those types of things. So all that kind of being like sidecar, queue control type of execution stuff. All right, so I'm taking a look here. Can't really see chat or whatever, but so I'll just march forward. Because next we have the demo. Okay, let's see how we want to do this. All right, first I'm just gonna show the pixel streaming again. Here's this demo app that Unreal provides to say, get started with pixel streaming. Here's a sample application we've built with this plugin, and it's a game environment, and here's some characters, and you can just check it out to test against your deployment, your architecture, and what have you. So what you see in this document, this reference sheet, this has been around a while, but is basically all the bits that we're going to show you here in our demo. And once again, if you're familiar with pixel streaming before this session, this all probably looks really familiar to you. So with that going, and my machine struggling, I'm gonna load up a session, start a stream. So here's our experience. You see we have the characters here. We have the ability to control and adjust some of the things in this experience, changing resolutions and some other parameters of the encoder on the back end. And then ultimately the game. So this is that same game that I talked about. Now, obviously we're over Zoom here, and my network is not the greatest usually. So we'll just bring this into full screen and see what it looks like. Maybe it looks like it's from the 1980s. I don't know, but I can interact with this. I can zoom in and out. This game doesn't have a whole lot of interactivity. It's just meant to show how the rendering is good and smooth, taking a look at some of the stats. And obviously you can imagine, a number of different things, whether it was a driving game or a simulator, or digital twin type of things with, using a headset or what have you. So pop out a full screen, kind of go back here, things that you would control are like frame rate. If I bring it down to 5, it's going to be really, really slow and jerky. Maybe that's how it looks through Zoom and all that. But found that 30 frames per second is pretty good through the web. And then different resolutions, so like knock it down to 720. It's a little fuzzier. 1080 is where we're encoding by default. So yes, this is pretty good. In any event, yeah, we'll see. Hopefully that looks okay to you, but it looks pretty good to me. Now in this demo, they show this little pull-out tab. I think somewhere in this doc, just so you can really look at some details. So get some metrics on bit rate, frame rate, how things are looking, test latency. So things are looking pretty good. It's a little higher than usual, but Anyway, so this is the experience. Now, if I go back and just look at this slide one more time, all of this is again is not unique to the application. The only part that's giving me that experience is this Unreal Engine and the web wrapper. So the web wrapper is like the controls and the typically just static elements and buttons or images tiles that I was clicking on to change in this scene here. And let me show you that too. I didn't do that, but I can change to different characters, and these interactions are like using that data channel to send signals to the game to say switch to character 3, 4, whatever, change to this outfit or that skin, and change to the different scene or background. That's right. So all those interactions are using the WebRTC data channel to communicate, send those signals to the streamer. So this wrapper, these buttons and tiles, those are all in that web or player view. And all you need to change out would be the HTML, the wrapper, and what you want in the game. Actually, in that URL, if we load it without this, without the demo.html, it's just a full screen view by default, and kind of bare bones. So that's how that looks. Okay, so back to the demo here. So we also have instrumented this pretty nicely, heavily, to where we have a Grafana dashboard that we built specifically for this to watch and track it. Now I see, well, we'll just look at this Grafana dashboard, right? I won't open the tab. Looks like people are plugging in that URL, and that's totally fine. We do have it capped right now at 2 active sessions. So if there are more than 2 people trying it right now, the reason why you are getting into a waiting situation is that it's just queuing you. That's what Matchmaker is doing, saying there's only 2 available. There are 2 people gaming right now. You have to wait. So in any event, what's shown here is our GPU workload, where we are on that GPU resource, and then total players, total streams, our stream utilization parameter. This metric for stream utilization is actually how we're doing horizontal pod auto scaling. So we try to basically always exceed the number of participants. So always have a proactive scaling ahead of the number of players actually playing, so that when player n+1 joins, they're able to get a stream right away. Naturally, right, if we exceed our worker nodes allotment here for number of total streams, we can scale the clusters, scale the node pool using the cluster autoscaler. So we don't have that configured on this one, but it's following those approaches just traditionally without anything special. Some other things you'll see here. Let's look bigger. So we see our turn services, so bytes transmitted. So it's running about 3.5 megs a second. So this is 1 player right now, so it's only about that, so it's pretty low. But that's showing and demonstrating the kind of the heavy network network bound component that is turn, establishing that relay between client and the stream. So typically our stream for bytes transmitted is going to be comparable to that, and maybe a little bit less if there are more peers on a single experience. So you can have more than 1 player in the same experience. And the last thing is bytes received So, sorry, turn is not collecting right now, but that's okay. Effectively, our stream bytes received is going to be very low. It's only sending the stream mostly, but when you have a big data component, it would show a lot more data received on the stream side too. Again, to that WebRTC data channel. It's cool. I'm glad people are in there poking around. All right. So, a note about GPU is that usually you can't overcommit a GPU. Here we are, and we're doing so in a way that really isn't wonderful for a true production deployment. The reason is that it's unpredictable, right? We can't control which stream is demanding more of the GPU. You can imagine they kind of step on each other's toes a little bit. The reason why we only have one is just to demonstrate a very minimal cluster here. So we have one worker node in each of those pools. So for the turn pool, it's just a single VM. Basically one of the least expensive shapes. Same with our general pool, single VM, and then our GPU is the V100 or the VM or GPU VM 3.1, and yeah, so that's what it has in its specs. So looking a little bit deeper, we have so again, there's 3 worker nodes. This is lens, so we're looking at the cluster a little bit now. And in our workloads, you can see we have 8 pods, 6 deployments, 1 daemon set, and according associated with them are our services, so 2 streams. Those should correlate with what we saw in Grafana. A traffic router, ingress, turn discovery, turn itself, and then matchmaker, the proxy layer, and the web player. So, yep, there are 6 deployments, and then our turn daemon set. Very cool. Okay, so let me see. So that kind of concludes the demo and the talk about what we've built here. Obviously, this is an assembly of a lot of different resources and informations that we've used to develop it, test it, validate it, and what have you. These originals from Unreal itself, the base images that we use, that they publish through Epic Games to build a container, all of which we put into a repo that, thanks to some folks, we have open source here from Oracle, and you can go check out. We are working on still some things for that, like Terraform configuration, so we can get a cluster set up, but all the information's in there on how we're doing this, and obviously the code as well. We have some links about what are the GPU offerings from Oracle Cloud Infrastructure, and just general about Kubernetes. And then what was just announced earlier or late last week was the Cluster API provider for OCI, which, if you're not using OKE, is a way to fully manage your own clusters through the OCI APIs in the open source way. So if you haven't already, take a look at some of these links, and we'll share this presentation and materials obviously after the call. So it looks like we've got about 20 minutes left, some of which we can use for Q&A. So I will, let's see, stop sharing. See what we have. Okay, let's see some chats. No Q&A. Some chat here. Okay. Good. All right. So who has questions? Anything they want to talk about or dive more deeply into? Okay. All right. All good. Well, thanks for attending. This was very fun for us to share, and we kind of encouraged to look at all the goodies that go with it. We have some fun stuff going on today. I think there's the Pi Day quiz. So if you want to test your knowledge of stuff you've gotten through the day that we've covered here in this presentation, you can take the quiz. And then also you can sign up for a free trial, and this is going to be resounding in all the presentations today. But yeah, there's some bonus credits and swag that can go with that. And for anyone who needs that link, I think you can use this. And then finally, there's some upcoming webinars on, and we have these often, but with regular cadence, so you can check out more ways to move your workloads and other stuff to OCI, and yeah, explore it a little bit deeper. Okay. All right. Well, with that, thank you for attending, and again, we'll share these recordings, make them available, and we hope you enjoy it.